In the last lecture, we used the normal distribution to help us answer some questions. And I was careful in every situation to include the words normally distributed. And that's because the tools that we're using, p-norm and q-norm and R, only work if our distribution is normal. Now the question is, what do you do when your distribution is not normal? Because we've seen distributions before that were either skewed left or skewed right. And even worse, in statistics, we often don't even know what the distribution looks like. Let me introduce two ideas. The first is the sampling distribution. Suppose we have a population that has mean mu and standard deviation sigma. That's the symbol mu, that just stands for the mean. That's sigma, that stands for standard deviation. So we have a population that has a mean mu and standard deviation sigma. And this is called a sampling distribution because we're going to take a sample. So say we take a sample of size n. And then we find the average. And the symbol for an average or a mean that you get from a sample is x bar. So we're going to take a sample size n and find the average x bar. So the example you should have in mind is, say we take a sample of 20 people and find their average age. Let me show you a demonstration. The picture at the top here represents the distribution of the population. The mean of the population is 25, standard deviation is 5. Don't worry about the median. And what I want to talk about here is what happens when I change the sample size. In other words, what happens when I change the number of people that I pick from my sample. So we're going to start off with a sample size of 1, so picking one person. And what I'm doing here is I'm picking a random person, find their age, and record at the bottom. Pick another random person, find their age, record at the bottom. Pick another random person, find their age, record at the bottom. And now I'm going to repeat this many, many times. And what I want to look at is the picture at the bottom and the mean and standard deviation for the picture at the bottom. So notice that the picture at the bottom looks about the same as the original. The mean, 25.0587, so roughly 25, roughly the same as the original, which was 25. Standard deviation, 5.0588, roughly 5, roughly the same as the original. Now, what happens when I increase the sample size? In other words, what happens when I increase the number of people that I pick? So let's increase this to 5. So we're picking 5 random people now. So pick 5 random people, find their average age, and then record at the bottom. Pick another 5 random people, find their average age, and record at the bottom. And then repeat this many, many times. Now look at the picture at the bottom. The picture changed. Now this picture looks more narrow. The mean, 24.9904, so still roughly 25, still roughly the same as the original. The standard deviation, 2.2136. So the standard deviation did now change significantly. The standard deviation got smaller. Standard deviation, remember, is a measure of how spread out our data is, so a smaller standard deviation should result in a picture that is more narrow. Now, what happens when I increase the sample size even more? So now let's increase the sample size to 10. So now we're picking 10 random people. Pick 10 random people. We're going to find their average age and then record at the bottom. Pick another 10 random people. Find their average age, and then we'll record at the bottom also. And now let's repeat this many, many times. Notice that the picture got even more narrow. The mean, 25.0053, so still roughly 25, still roughly the same as the original. Standard deviation, 1.5881. So standard deviation got even smaller. With sample size of 5, it was around 2 something. Now with a sample size of 10, it got even smaller to 1.5881. So what we saw here was that when we changed the sample size, when we increased the sample size, the mean stayed about the same as the original. The standard deviation, though, got smaller. Let's write down what we just saw. So what we just saw was that when we take a sample and look at the averages, these averages so this refers to the picture at the bottom. So these averages has a mean. I'm going to write this as mean sub x bar. So this just refers to the mean of the bottom picture. So the mean of the bottom picture was always the same as the original population. Okay, so the mean of the bottom picture is the mean of the original population. The standard deviation, though, we saw changed. So the standard deviation of the averages, so standard deviation of the bottom picture, we saw that it got smaller when the sample size increased. So mathematically what's going on is the standard deviation of the averages is the standard deviation of the original population divided by square root of n. So if your sample size is bigger, so if your n is bigger, you would be dividing by a bigger number. So overall, you'll get a standard deviation that is smaller. And that's the one fact that we'll need about the sampling distribution. Let's say our population looks like this. So this distribution is very skewed. Skewness, remember, refers to the location of the tail. The tail here is on the right side. So this is a distribution that is heavily skewed to the right. Let's look at what happens when we increase the sample size here. Let's start with a sample size of 1. Notice that the picture at the bottom looks roughly the same as the original. So still heavily skewed to the right. Now what happens when I increase the sample size to 5? What do you think happens? The picture now is less skewed to the right, right? You may say it's still slightly skewed to the right, but it's definitely less skewed to the right now and looks more like a normal distribution. What happens if I increase the sample size now even more? Let's go to 30 now. The picture at the bottom now doesn't look skewed at all. It looks very much like a normal distribution. Let's try what we just did on a wild picture that looks like this. So starting with a sample size of 1, what do you think the picture would look like? With a sample size of 1, I'm expecting the picture to look the same as the original. And it does. Now what happens when I increase the sample size to 30? What do you think the picture would look like? The picture now looks like a normal distribution. And that's the big idea in statistics. No matter what the original population looks like, as long as you pick a sample size big enough, and big enough for us is going to be 30, and look at the averages will always look like a normal distribution. What we just saw is called the central limit theorem, and I think this is the most important theorem in all statistics. And it says, if n is bigger than 30, in other words, if the sample size is bigger than 30, then the average is x bar, in other words, the picture at the bottom, will be approximately normal. With mean, so this is saying the mean of the picture at the bottom, so the mean of the averages is the original mean of the population. the standard deviation of the averages, so standard deviation of the picture at the bottom, is the original standard deviation of the population divided by square root of n. Okay, if you pick a sample size big enough, bigger than 30, and look at the averages, those averages will be approximately normal, and it will have mean and standard deviation this. So that answers the questions that we had at the beginning of the lecture. What do you do when your distribution is not normally distributed? And the answer is, as long as you are picking a sample size big enough, bigger than 30, and look at the averages, the distribution will be normal. And most of the time in statistics, we're taking samples and collecting data because we don't know something about the population. Most of the time, we don't know what the population distribution looks like. And central limit theorem says, who cares? We don't care.
We do not care.
As long as you pick a sample size big enough, bigger than 30, and look at the averages, the distribution will be normal. And that's why normal distribution is so important in statistics. The diagrams at the bottom here are the same diagrams that I used in the last lecture. So in terms of solving problems, the only thing that's really new today is this box. And this box refers to what mean you should use and what standard deviation you should use if you are picking more than one person, if your sample size is more than one. So if your sample size is more than one, the mean is going to be the same as the original mean. So in other words, you don't change that. The standard deviation, you will change. So you will take the original standard deviation and divide it by square root of n. So really the only thing that's new is going to be the standard deviation. So if you're picking more than one person, in other words, if your sample size is more than one, you will have to adjust the standard deviation by taking the original standard deviation and dividing by square root of n. Everything else will be the same as in the last lecture. Speaking of the last lecture, remember I said there are those 3 P words: probability, percent, proportion. Anytime you see those P words, you should think area. So let's now try some examples. Example 1. The mean distance that commuters in the US travel each day to work is 16 miles. The standard deviation is 8 miles. If 75 commuters is chosen, there is a 94% probability that the mean commute distance is between what 2 values? Just like in the last lecture, the first thing I'm going to do is I'm going to draw a normal distribution picture and put the mean in the middle. Why are we allowed to use the normal distribution here? Notice that we're picking 75 commuters. In other words, our sample size here is 75. 75 is more than 30. Central limit theorem says as long as your sample size is more than 30, yes, you can use the normal distribution. The mean here is, mean distance is 16. 16. And then I'm also going to label what this x-axis represents. So this x-axis has the 16 on it. 16, what is this 16? 16 what? Miles. So this x-axis is miles. Or you can say commute distance. So anytime I see miles or commute distance, I know that's talking about an x. The next thing I need to decide is whether this is a x to area or an area to x problem. So let's take a look at the last sentence there. If 75 commuters is chosen, there is a 94% probability that the mean commute distance is between what 2 values? So what do I want at the very end? I want 2 values. And this 2 values is referring to commute distance, right? I'm looking for 2 commute distances at the end of the question, right? Commute distance, distance is miles, miles are x's. So I'm looking for 2 x's at the end of the problem. Which means this should be the one that ends with an x. So x to area or area to x. Area to x. Another way to think about it is looking at this last sentence, what is it that I'm giving you in that last sentence? If 75 commuters is chosen, so 75 refers to how many people I'm choosing, that's going to be the sample size. There is a 94% probability, okay? Probability. Probability is one of those P words that I said you should pay attention to. Probability refers to area. Okay, so probability, percent, proportion. Anytime we see those P words, think area. So I'm starting you off with 94% area. So I'm giving you an area to start. So if I start you off an area, which one starts with an area? Area to x starts with an area. The next thing I need to decide is draw the rest of the picture and decide whether it's shaded left, shaded right, or shaded between. This one obviously is going to be between. Okay, so this is shaded between. And let me put this 94% on my picture. So that 94% is an area. So that doesn't go on the x-axis, that goes up at top here. It's going to be between. And that 94%, we always convert the percents to decimals when we compute things. So 94% as a decimal is 0.94. And we're looking for the two x's, the two commute distances, that has a 0.94 area between. Now, today, I'm going to add one extra step, which is to write down this box. In other words, I'm going to list out the mean I'm going to use and the standard deviation I'm going to use. And what the box says is that the mean is going to be the original mean of the population. So in other words, whatever mean is in the problem. So the mean in the problem was this 16. And really, I should write mu subscript x bar, sigma subscript x bar. But I'm going to be lazy and not include those. Standard deviation is going to be the original standard deviation divided by square root of n. And n is our sample size. The original standard deviation is 8 divided by square root of the sample size. In other words, how many people are we picking here? We're picking 75 people. All right, so let's go ahead and do that on a calculator. 8 over square root of 75. 8 over square root 75. And round these intermediate steps to 3 decimal places. So that's 0.924. Okay, the rest of this problem is going to be the same as what we did in the last lecture. The only difference is just make sure for the standard deviation you're using 0.924 and not 8. Okay, so this is going to be the same as what we did in the last lecture. So if you need to, go back to the last lecture and look for an example that's of this type, area to x shaded between. So in the last lecture, I tagged each problem with the type of question it is. So that's an x to area shaded to left. Let's look for an x to area or area to x shaded between. Area to x shaded between, which is example 6. So if you need to, go back to that example. It's going to be the same exact steps. All right, area to x. First thing I need to do is go from area to z by doing a Q norm. Q norm left area. Okay, so we're going to Q norm the left area. 0.94 is the area between. That's not the left area that I need. I need this white part in this picture, right? The left white part. So the way you do it is you're going to do 1 minus 0.94. Okay, 1 minus 0.94. 0.06. Okay, 0.94 is the area in the middle. If you do 1 minus 0.94, that gives you the area of the white part, so both white parts. Because I just want the left one, divided by 2. So 0.06 divided by 2. Pretty sure that's 0.03. Okay, 0.03 is the area of this white left part. That's what you plug into QNorm. So we're going to do QNorm in R, 0.03. Negative 1.881. And if I look at my diagram, QNorm goes from area to Z. Okay, so what QNorm spit out there is a Z. And because I'm looking for two X's at the end of the day, I need two Z's. So that negative 1.881, okay, that refers to the one on the left. There should be also one on the right, which is going to be just the positive version of that. So positive 1.881. Okay, we just went from area to Z using QNorm. Next step is to go from Z to X using the X formula. Okay, so we're going to do the X formula for both of these Z's. So the formula says X equals mu, the mean. The mean is 16, plus Z times the standard deviation. So plus negative 1.81 times the standard deviation. So remember here, use this standard deviation that you found here, 0.924. Okay, and not the original 8. Okay, so if you have a sample size, if they give you a sample size, which we do here, 75, you will have to adjust the standard deviation and use the adjusted standard deviation. All right, so let's enter that into a calculator. 16 plus negative 1.881 times 0.924. 14.262. Okay, that's one of the answers I want. Do the same thing for the other Z. So X equals the mean, which is 16, plus Z, 1.881, times the standard deviation, 0.924. And on the calculator, 16 plus positive 1.881 times 0.924. 17.738. Example 2. Typing speed is approximately normal with a mean speed of 45 words per minute and a standard deviation of 10 words per minute. What is the probability that a random sample of 12 people have mean typing speed of more than 40 words per minute? First thing I always do is draw the normal distribution picture and put the mean in the middle. We're picking 12 people here, which is less than 30. So are we allowed to use the normal distribution here? And the answer is yes. If your sample size is less than 30, then you have to know that the population is normal in order to use normal distribution. So we are told here that typing speeds are approximately normal. So we're good. Our mean here is mean speed of 45. And then I'm always going to label what that x-axis represents. So the 45 here is words per minute. Or you can say typing speed. So anytime I see words per minute or typing speed, I know that's referring to an x. Now the next thing I need to decide is this an x to area or an area to x type question? Okay, so let's look at the question here. So what is the probability that a random sample of 12 people have mean typing speed of more than 40 words per minute? Okay, I see. What is the probability? So I want probability at the end of the day. When I finish the question, I want probability as my final answer. Probability, that's one of the P words that represents area. So I want an area at the end of the question. So which one ends with an area? X to area. This is going to be an X to area question. Another way to think about it is what information am I starting you off with? Okay, so the question says, what is the probability that a random sample of 12 people, so 12 there is just the sample size, have mean typing speed of more than 40 words per minute? So I'm giving you that 40 to start with, 40 words per minute. Words per minute, that's on the x-axis. So that 40 that I'm starting you off with there, that's an x. I'm starting you off with an x, so which one starts with an x? X to area. So it's an x to area question. Next thing we need to decide is this shaded left, shaded right, or shaded between? More than. Okay, more than tells me this is going to be to the right. So I'm going to put 40. 40 we said was an x. 40s will be on the left here. And it says more than, so more than will be to the right. This is shaded to the right. Now the one new step today is I'm going to write down the mean and the standard deviation that I'm going to use. So the mean is going to be the same as the mean of the original population. So whatever mean is in the original question. The mean was 45. The standard deviation, I'm going to have to adjust. So standard deviation will be the original standard deviation. So standard deviation 10 divided by square root of the sample size. So sample size, how many people are we picking here? 12 people. And let's calculate that. So 10 over square root of 12. Okay, round this to 3 decimal places. That's 2.887. So when I do the rest of the question, just make sure that I'm using standard deviation of 2.887 and not the original 10. This is an x to area shaded right question. If you need to, go back to last lecture and look up an example that is x to area shaded right. The steps will be the same. Okay, this is x to area. First thing I need to do is x to z using the z-score formula. So z equals formula says x, our x was this 40, minus mu, so minus the mean is 45, over the standard deviation, okay, make sure we are using the adjusted one, 2.887, and not the original 10. All right, so on our calculator, up top, 40 minus 45, on the bottom, 2.887. Round to 3 decimal places here, that's negative 1.732. We just did x to z by using the z-score formula. Next step, z to area by doing a p-norm z. So next, we're going to do a p-norm on this z, which was negative 1.732. So in R, p-norm, negative 1.732. Round to 3 decimal places, this is 0.042. Okay, the way p-norm works is you feed it a z, and it spits out the left area. So this 0.042 is the left area. Are we looking for a left area here? No, we're looking for the area to the right, right? So this 0.042 refers to this white part on the left here. If I want the other side, 1 minus. So as the very last step, we do a 1 minus 0.042 to get the area to the right. $0.958. Example 3. The mean hourly wage of people in California is $14 with standard deviation $8. A pollster draws a sample of 60 people in interview. there's a 32% probability that the mean hourly wage of the people in the sample is greater than what value? The first thing I always do is draw the normal distribution picture and put the mean in the middle. The mean here is $14. And then always label the x-axis. So our x-axis has this 14. What does this 14 represent? That 14 is dollars. So you can put dollars, or you can put the dollars actually is referring to the mean hourly wage. So you can also put hourly wage. So anytime I'm talking about hourly wage or dollars, I know it's an X. The next thing I need to decide is whether this is an X to area or an area to X. Okay, let's read the last sentence. There's a 32% probability that the mean hourly wage of the people in the sample is greater than what value? So notice that in that last sentence, I'm starting you off with a 32% probability. So I'm giving you a 32% probability to start. Probability is one of those P words that I said you should think area. I'm giving you an area to start. Which one starts off with an area? Area to X. Okay, so this one would have to be an area to X. Another way to think about it is I want what value, so I want what value when I finish the problem. Okay, so that what value is referring to what hourly wage. So I want an hourly wage when I finish the question. Hourly wage, dollars, is talking about X's. I'm looking for an X when I finish the problem. So which one ends with an X? Well, area to X ends with an X. So this is an area to X question. The next thing I need to decide is whether this is shaded left, shaded right, or shaded between. It says greater than. Okay, greater than tells me that this is going to be to the right. Okay, so this is shaded to the right. Okay, let me draw the rest of the picture. Shaded to the right, I need to put this 32% on my picture. That 32% is an area, so that doesn't go on the x-axis. That's going to go up top here. It's going to be to the right. So to the right, 32% is this area to the right. 32% as a decimal, 0.32. And then I'm looking for an x that has an area of 0.32 to the right. Now, I'm going to write down the mean and standard deviation that I'm going to use. That's the new thing in this in today's lecture. The mean I'm going to use is the same as whatever is the original population, 14, 14. Standard deviation, you usually are going to have to adjust that. So our standard deviation is going to be the original standard deviation, which is the 8, divided by square root of the sample size. So how many people are we choosing? Supposed to draw a sample of 60 people, 60. Okay, so let's go calculate that. 8 over square root of 60. Okay, round to 3 decimal places. This is 1.033. Okay, so this is a area to X shaded right. So same process as in the previous lecture. The only thing different is just remember to use the adjusted standard deviation instead of the original standard deviation. Okay, so we'll be using 1.033 as our standard deviation. Okay, area to X. First thing I need to do is area to X. I need to do area to Z by doing a Q norm left area. Okay, I need the left area to plug into Q norm. It's not going to be 0.32. 0.32 is the area to the right. That's not the left area. So I need the left area of the picture, which is this white part. To get the white part, I just need to do 1 minus 0.32. Okay, 1 minus 0.32. 0.68. Okay, so 0.68 is the area to the left, the white part. That's what I need to enter into R. Okay, so in R, Q norm, 0.68. Okay, Q norm takes an area and it outputs a Z, so that's a Z. So our Z is 0.468. Right, we just did area to Z by doing Q norm. Next step, Z to X by using this X formula. X formula. So X equals mu, the mean. Our mean here is 14. Plus Z, 0.468. Times the standard deviation. Remember, we're going to be using our adjusted standard deviation, 1.033, and not the original. Okay, plug that into our calculator. 14 plus 0.468 times 1.033. 14.483. Example 4. The mean cholesterol level of US adults is 202 with a standard deviation of 41. What is the probability that a randomly chosen adult's cholesterol level is between 190 and 200? First thing I always do is draw the normal distribution picture and put the mean in the middle. Our mean here is 202. And then label what the x-axis represents. So the x-axis has this 202. What is this 202? This 202 is a cholesterol level. So now I know that anytime I'm talking about cholesterol levels, it's an X. The next thing we need to decide is this an X to area or an area to X? So let's read the last sentence here. It says, what is the probability? Okay, probability is one of those P words that I said you should think area. What is the area? So I want area as my final answer. So I want area when I finish the question. Which one of these ends with an area? X to area. So this is X to area. Another way to decide is to read that last sentence and look at what else I'm giving you to start with. What is the probability that a randomly chosen adult's cholesterol level is between 190 and 200? So what is this 190 and 200? Are those X's or are those areas? 190 and 200, those are the cholesterol levels. Cholesterol levels on my x-axis, those are X's. So 190 and 200 are both X's. So I'm starting you off with X's. So which one starts with an X? X to area. Okay, so that's another reason why it's an X to area. Now I need to decide whether this is shaded left, shaded right, or shaded between. Definitely between. Okay, so this is shaded between. And then let me draw the rest of this picture. The 190 and 200, we already said were X's, so they should go on the X-axis. 190 and 200 would be both on the left of this 202. And we said we were looking for the area between. Okay, so this is a X to area shaded between. The one new step in today's lecture is I'm going to list out the mean and standard deviation before I do the rest of the question. The mean, okay, the mean is always going to be the same original mean as the population. So the mean for the population is this 202. The standard deviation, we will have to adjust. So the standard deviation is going to be the original standard deviation of the population divided by square root of n. What is the standard deviation of the population? The original one. Standard deviation of 41. Divided by square root of n, the sample size. So how many people are we choosing here? What's the probability that a randomly chosen adult cholesterol level is between 190 and 200? So notice that unlike the other questions, I didn't put a number here for how many people we're choosing. So if you don't see a sample size, we're going to assume that we're picking one person. And that's really the only thing I wanted to point out in this example, is that if you don't see a sample size given, we're going to assume it's 1. So 41 divided by the square root of 1. If you do it on a calculator, you'll just get 41 again. And now the rest of the question, which I won't finish, the rest of the question will be an X to area shaded between question. So if you don't remember how to do it, go back to the original, or go back to the last lecture and look for an X to area shaded between. The steps will be exactly the same. All right, have a great day. See you next time.